Now, the reason to focus a minute on pumping examples is not just they're predominant in process plants, they're predominant everywhere. Pumping is the world's biggest use of motors. Fans, which have the same physics, are the second biggest. Together, fans and pumps use half the motor electricity, and motors use 3/5 of all electricity, even more in Singapore. A big motor running all the time uses its capex worth of electricity every few weeks. And there are 35 things you can do to motor systems to save about half their electricity very cheaply, because if you buy the right 7 things first, you get 28 more savings for free. But before you attack the motor system, you should start further downstream in the torque requirement, and further downstream than that in, for the case of a pumping system, flow and friction. Now, that's, of course, one thing to do for a big plant where there are obvious opportunities of many kinds, but let me just feature the pumping systems out of this larger list, since electricity is the costliest form of energy and the most lucrative kind to save. So if I feed 100 units of fuel into a classical power plant and lose most of it at the plant and more in the grid and more along the way, I only get 1/10 that much energy coming out the pipe as flow. Every unit of flow or friction I can save in the pipe will save 10 times that much fuel cost, pollution, and global warming back at the power plant. And it will make the motor, for example, 2.5 units smaller. So as I go back upstream, I compound the savings in energy and in capex, making the equipment smaller, simpler, and cheaper. I don't know any engineering text that tells us to start downstream, but it's a very fundamental way to multiply your savings. So if we think about flow, let's first try to get rid of the flow that's causing us to do the pumping. I was working in a big LNG plant where they're trying to make minus 161 initially Celsius liquid methane in a blazing desert. And I was walking around with my weapon of choice, which is an infrared thermometer, pointed at the ground, rather to the puzzlement of my hosts, until I pointed out that the ground was covered with several hectares of dark asphalt and gray concrete up below the cryoplumbing that they're trying to make extremely cold. What's wrong with this picture? So then we did some regressions on how the plant works in different weathers, and we found that each Celsius degree by which we could cool off the site by putting something light-colored and cheap on the ground would save 106 million Aussie dollars present value, and altogether there was about $1 or $2 billion worth lying on the ground, literally, because we could make the site 10 or 20 degrees cooler. And then we found that the cryo pipes were insulated, of course. You can argue about how well they should be insulated. And then they were covered with shiny stainless steel. There's something odd about stainless steel, which I confirmed by doing some infrared measurements. Let's try a little thought experiment. I've got 3 pieces of sheet metal here sitting in the hot sun. One of them is bright bare metal, another one's painted white, another one's painted black. Which one will get hottest? The black one. Who votes for black? Who votes for the white one? Who votes for the bare metal? Because stainless steel has terrible infrared emissivity, so it has to get really hot before it can cool off. They would have been better off painting it black, although white paint costs the same. How about an ice cream plant? Sorry to dwell on ice cream. Must be something about the weather. And I visited one that had best-in-class equipment, but then I noticed that the insulated box containing the pipes that you're trying to make very cold to turn cream into ice cream also contained a couple of 250-horse motors and the compressors they drive. So all the waste heat was going into the same pipes you're trying to make cold. You know, you don't have to be a rocket scientist to figure out what's wrong with that one. We often find choke flow, throttling valves, throttling vanes in cube law machines. It's even worse than trying to drive your car with the accelerator floored and just control speed with the brake. Or how about when we're doing a lot of cooling we don't need to do because we didn't design the building properly? Well, one of my favorite examples is a runaround pumping loop. It could perfectly well have been a chilled water or a condenser water loop, but this was for heat transfer in a factory. And the top German firm optimized it to use 71 kilowatts. And then with some ideas from Mr. Lee, we took it to a Dutch engineer who designed it at 5.3 kilowatts, 92% less. And it cost less to build. It worked better because of two changes in design mentality. The first was to use big pipes and small pumps rather than small pipes and big pumps. The friction in a pipe goes down, is nearly the fifth power of its diameter. And the engineering textbooks tell us to make the pipe just as fat as will repay its greater capex over the years from the saved pumping energy. But this is methodologically just as wrong as not counting the ability to eliminate the furnace in my house when you think about how much insulation there should be. Because after all, the pumps, the motors, the inverters, the electricals all have to be big enough to overcome the friction in this piping system. So their size and roughly their capex will go down as nearly the fifth power of pipe diameter. But the fatter pipe costs more as only about the second power of diameter. So when we conventionally optimize the pipe as a component by itself, we're pessimizing the system. If we optimize the whole thing together, we'll use fat pipes, tiny pumps and motors, and the total capex will go down. Not rocket science, just good Victorian engineering rediscovered. Another lesson we learned from Mr. Lee is to lay out the pipes first, then the equipment. Normally, of course, we do it the other way around. We put the equipment where we're used to, and then we call in the pipe fitters to hook it up. But by then, of course, there's so much in between, and it's so far apart, and they're all at the wrong height, facing the wrong way, that by the time the pipe gets all the way across, dressed at neat right angles, it has 3 to 6 times the friction that it should have had with a short straight shot. The pipe fitters think this is great. You pay them by the hour. They mark up the pipes and fittings with extra profit. They're not paying for your bigger pumping equipment or electric bill. But for you as owner, it's better to have fat, short, straight pipes than thin, long, crooked pipes. And in this case, factor 12 reduction in pumping energy, less capex, and as a free bonus, 70 kilowatts less heat loss because it's easier to insulate short, straight pipes. But I'm afraid we botched the job by not counting 7 additional benefits. The system will now be smaller, lighter, quieter, have a cleaner layout for easy maintenance access, need less maintenance because there's less to go wrong, have higher uptime, and last longer because there aren't so many elbows being eroded away over time by fluid turning a corner. I did a rough calc that we would have saved another factor 4 if we'd counted those benefits as well, and it would have cost even less. The more benefits you count, the better solution you get. And this case is archetypical because practically everything we've got in our society that uses energy, including especially process plants, tends to be designed optimizing single components for single benefits rather than whole systems for multiple benefits. And if we get that right, we typically save half to 1 order of magnitude on energy and water and other resources, typically with lower capex and better performance. Hence the need for the casebook of vivid examples of this sort. And if any of you are or know of practitioners who have such good examples of factor 4 or 10 energy savings with lower capex through whole system design, please let me know. I'd like to feature those in our casebook, especially in this climate with the cost of drying the makeup air. Now, once you've minimized the flow required in, say, a pumping system, suppose it's a chilled water or processed water system, then we minimize the friction to deliver it. Very often you see a pair of pumps, either helper pumps or ones an in-place spare for a critical pump. They're laid out like this because they're drawn like this, then they're built like this. So all the time the flow goes through 2 right angle bends, extra friction, then it goes through 2 valves. Why don't we do it with no bends and no valves or 1 valve? Well, we're just not used to it. It's different. But Peter Rumsey, a protege of Mr. Lee's, colleague of mine, did that as a retrofit and saved 3/4 of the energy in this condenser water system, notice he has not just a Y joint, but a sweep bend with a pipe running diagonally through the air because he correctly instructed the pipe fitter to lay out the supply pipes as if they were drains. Drains, of course, with right angles will clog. Plumbers know that. And he also got rid of 15 pumps. They will never again waste electricity in maintenance. Negapumps are a wonderful kind to have. So the result was on the retrofit of that museum, he ended up saving 5/8 of the annual cost whilst doing very little to one of the pumping systems and only a bit to the cooling towers. After a while, you develop special Muda spectacles. Take a look at this little tank back here and what happens to its pipe run. I figured if that tank had been rotated 30 degrees around its vertical axis, we could have eliminated 11 bends. When you start taking a careful look at process piping layout, it's obvious that whoever designed this stuff was thinking about something else. And perhaps they were paid by the bend. The best example I know is actually from a brilliant engineer at Stone & Webster who was doing a bit of an ethylene plant, and by untangling the layout, he was able to reduce the number of elbows from 29 to 3, and these were half-meter diameter stainless elbows. So he was a very happy camper. Here's a common error. I'll bet many of us have designed piping runs like this to bring back water from a cooling tower to a chiller. How about doing it this way? Everything gets better. It just requires thought because it's different than what we're used to doing. Big pipes, small pumps, very few bends, sweep bends, Y bends, much less space, weight, friction, energy, fewer parts, less installation, smaller parts, less O&M, higher uptime. Everything gets better. How often can we do that in process piping layouts? Quite often. And making things the right size is really critical. Normally, fab designers assume that tools are going to use about 2 to 5 times the energy they actually use. This is partly because of safety margins and partly because load diversity is ignored. Not everything's running flat out at the same time. Typical duty factor is 30 or 40% in many fabs. So this means that the phantom loads we designed for that don't actually occur cause us to buy hundreds of extra tons with a whole system cost approaching $2,000 and incur the part load penalties of the oversized system. And when we have inflated load estimates, that means deep coils, big pressure drops, oversized fans. The fans end up heating the air as much as the tools do, and then everything else gets bigger as well. So CapEx goes up right across the board because the initial sizing was not done really well, and then there's extra OpEx as well to support those assets. I think Mr. Lee once remarked that if we designed fabs, or if we designed jumbo jets the way we design ship fabs, they would have 4 extra sets of landing gear, 3 are spare just in case, and they'd have 2 extra sets of engine and so on, and they'd never get off the ground. But of course, in designing a jumbo jet, we do actual measurements of what loads we have to meet, because it all has to get up in the air.